Okay, thanks everyone for coming to my talk, or for just continuing to exist in this room. My name is Jasper. I'm from the University of Calgary in Canada. Today I'm going to talk about the nucleotide diversity at neutral loci that are flanking a divergently selected locus. So a common pattern in population genetics is that of a selective sweep, where an allele under strong positive selection rises to frequency, fixes, and eliminates a whole bunch of the variation in neighboring loci that are under strong physical linkage. So we can visualize that here, where the relative polymorphism at a neutral locus is greatly depressed nearby the selected locus. And then as you move away from that selected locus, and recombination rates increase, eventually the relative polymorphism increases and returns back to the genome-wide baseline levels. There's been much interest in recent times in using genomics to look across the genome and identify signatures of selective sweeps by finding regions of reduced diversity. However, not all adaptation is global. In complex heterogeneous environments like the one seen here in Banff National Park, you can actually have different areas of the overall landscape that maintain different locally beneficial alleles. When this happens, we can actually find a pattern that's completely opposite to the pattern we'd expect from a selective sweep. So in heterogeneous environments, migration and selection can interact to maintain locally adapted loci, and we can actually get a great peak in nucleotide diversity nearby that selected locus. And then as recombination rates increase, that peak in diversity eventually decays back to the genome-wide baseline levels. So here's the puzzle then. If selective sweeps erode diversity, and local adaptation can apparently increase diversity, what kind of nucleotide scale patterns should we be expecting across the genome? So my research question more explicitly then was, how is the nucleotide diversity at a neutral locus affected by its distance to a divergently selected locus? To investigate this, I performed a simulation study. I used a forward-in-time, individual-based stochastic program called NEMO. For the results I'll share with you today, I just used one diploid chromosome, one selected locus, and then that one selected locus was flanked by 74 neutral loci. In today's results, I'll just show a simple two-patch model with symmetric migration. And then to approximate a heterogeneous landscape, I used divergent selection, where an adaptive allele was positively selected in one patch, negatively selected in the other patch, and then the alternate adaptive allele was just selected in the reverse manner. So I ran my simulations for 10,000 generations of random mating, mutation, migration, and selection. And then after 10,000 generations, I assayed the nucleotide diversity at each locus across the chromosome. Then I just regressed the nucleotide diversity at a neutral locus on its distance from the divergently selected locus. So just for example, so here's nucleotide diversity on the Y, and then the distance from the selected locus on the X. So your selected locus would be right here, and then that's moving away from it. So say in this example data, we got a pattern like this, where there's a positive association. This might suggest to us that diversity is being eroded nearby the selected locus. If we found a pattern like this, where there's a negative association between diversity and distance, this might suggest to us that diversity is being increased nearby that selected locus. All right, now what I'm going to do is I'm going to take the slope from this, not this data, but the slope of this relationship, nucleotide diversity, by the distance from the divergently selected locus, and I'm going to stick that here on the Y. So this Y-axis is the slope of nucleotide diversity versus distance to the selected locus. On the X, it's the migration rate. In the color, it's the strength of selection. I've used VS as my metric for the strength of selection, where a VS of 2 is really strong selection, and a VS of 1 billion is selection so weak that it's effectively neutral. So I hope that makes sense so far. the first thing I want to look at here is just this red dashed line is the 0 line. So there's two broad patterns so far. There's everything in this migration selection parameter space where things are positive, and then everything in this migration selection parameter space where things are negative. So I first want to look up top. Up here, there's a positive association between nucleotide diversity and distance to that divergently selected locus. So in this region of parameter space, either diversity is being eroded nearby that selected locus, or diversity is being increased far away from that selected locus, or a combination of both. In contrast to that then, in this parameter space, either diversity is being increased nearby that selected locus, or it's being decreased far away from that selected locus, or a combination of both. All right, I'm going to leave this guy and come back to him in a sec. Here, the y-axis is much easier. It's just the mean per locus nucleotide diversity as we look across the chromosome. Again, migration rate on the x, strength of selection in the color. So the first thing I want us to note here is this green line here. So this is from a VS of 1 billion. So this is where selection is so weak that it's effectively neutral. So this green line gives us the drift expectation for the per locus nucleotide diversity. Selection is so weak that we can basically ignore it. So that gives us two regions of parameter space, or two different patterns to explore. There's this region here, where we're below the green line. So here we basically have less nucleotide diversity per locus than you'd expect through drift alone. So it looks like something in this region of parameter space is eroding diversity. Up here, it's the opposite. So we have more diversity per locus than we would expect through drift alone. So it looks like up here, we're actually increasing nucleotide diversity. I want to put both those same two figures side by side now, just to synthesize things all together. So first let's look at this parameter space. Here we have a positive association between nucleotide diversity and distance, and we have less diversity per locus than we would expect through drift alone. So taken together, it looks like we're eroding the nucleotide diversity nearby that divergently selected locus. So in this region of parameter space, it looks like selection is effectively purging migration load faster than migration can input new variation into the system. The complete opposite then, in this migration selection parameter space, now we have that negative association between nucleotide diversity and distance, and we have more nucleotide diversity per locus than we would expect through drift alone. So in this region of migration selection parameter space, it looks like we have an increase in nucleotide diversity nearby that divergently selected locus. Okay, there's three main takeaways that I hope we can all leave with. The first is that the nucleotide diversity of a genomic region that's nearby a divergently selected locus may decrease in certain regions of parameter space or actually be increased in other regions of migration selection parameter space. Because of this, there's no clear nucleotide scale prediction for local adaptation. A divergently selected locus might be decreased in nucleotide diversity in one region of parameter space, but that exact same locus would actually be increased in diversity in a different region of migration selection parameter space. And then finally, for detecting the nucleotide scale signatures of selective sweeps, it may depend on the time since the sweep occurred, or the time since that beneficial mutation occurred. If you're in the region of migration selection parameter space that actually causes or results in an increase of diversity nearby that selected locus, right after you have a new mutation and that sweep occurs and fixes, you would expect a trough in diversity, where that sweep has eliminated all that diversity. Then as time goes on, eventually recombination will return all that neutral variation. And then as further time goes on, eventually you'll get that peak in diversity, like we saw in that one region of parameter space. So at the same exact locus, early on you might expect a trough, and later on you would actually expect a peak in diversity. So real quick, I just want to thank my supervisor, Dr. Sam Yeaman, everyone in the Yeaman group, shown here, and my home university, and NSERC for funding. Thanks very much. Yeah?
I think I missed it. When you measured nucleotide diversity, was it in each individual population average, or was it in the pool of the two populations?
It was just one, each population, yeah, yeah. Like, all the two populations were symmetrical here, so it didn't matter, but other times they're not. Yeah?
Maybe this is a dumb question. What's
No.
V in VS?
Oh, it's just the variance of the fitness function.
Okay, do you have any sort of intuition for what might be a plausible zone of that VS parameter in, like, your average local adaptation? Presumably it would be smaller than a billion.
Yeah.
Oh, where's the
yeah.
limits?
I think that yeah, for the VSs, the first VSs I used were 2, 5, and 10, and this is how much academic integrity I put into it. I copied what other people had used. That was the extent of my thinking. Yeah, but VS of a billion is definitely neutral because we see here there's no relationship at all between diversity and distance. And that's the end of my answer, yeah. Okay, thanks so much, guys.